Today we have the third lecture of the atmosphere module. We're going to be talking about atmospheric temperature and pressure, but really it's going to be mostly a focus on pressure in the atmosphere. So the goal today is to understand the vertical profile of pressure in the atmosphere and explain how pressure and the resulting barometric law results in the sea breeze circulation. So to quickly recap, yesterday's lecture, we talked about the various layers of the atmosphere, and the bottom layer closest to the surface of the Earth is the troposphere. It's down here. It's characterized by decreasing temperature with height, and so that's because it's increasing distance away from the Earth, which is warmed by the sun. The troposphere contains almost all of the atmosphere's water vapor, but it's a fairly small fraction of the atmosphere's total height. It goes up to about maybe 10 to 15 kilometers. So not super high. And then above the troposphere, we have the stratosphere, which is the opposite temperature relationship. Temperature increases with altitude. And that's because most of the good atmospheric ozone is sitting in the stratosphere, and that ozone is absorbing UV radiation, and it's warming as you go up throughout. And there's very little vertical mixing in the stratosphere. And these are what we presented as the vertical profiles of pressure and temperature. Now just going as high as the mesosphere. Going as high as the mesosphere here. And you can see there's this sort of flip-flopping of temperature with altitude, and we use those temperature inversions to define the layers of the atmosphere. Whereas with atmospheric pressure on the left, you can see it's quite different. The scale is different. It's much, much larger than the temperature scale, and the relationship is much different. It doesn't do any of this flip-flopping back and forth. Okay, so let's focus in on this pressure issue. So again, here are the temperature and pressure profiles. And something to note is that the temperature doesn't really vary a lot. Maybe from just above 200 Kelvin to 280 Kelvin, you might think, well, that is a lot. But compared to the fact that pressure varies by 6 orders of magnitude, just from the surface of the Earth to the top of the mesosphere, by that context, temperature doesn't really change much at all. So when we're doing pressure-related calculations, and we're going to do some fairly simplified pressure calculations today, for the most part, we assume that temperature is constant, and that's a safe assumption because pressure is varying wildly. It's huge changes in pressure, and there's fairly narrow changes in temperature. So the definition of atmospheric pressure is it's the pressure that you experience at any height in the atmosphere due to the force per unit area exerted by the weight of all of the air lying above that height. So the way I always think of it is that when you're standing on the surface of the Earth, you've got the entire atmosphere weighing down on you. If you could take an imaginary elevator up a couple of kilometers, you would have less of the atmosphere sitting, weighing down on your head, and so there's less pressure at that height than there is at the surface. So atmospheric pressure continuously decreases with increasing height above the ground. And that's why, of course, we don't have any inversions in the pressure profile like we do in the temperature profile. This can be also explained using a fairly simple little box model here. So we've got a blue slab of the atmosphere. It sits at some random altitude z. The bottom of the slab sits at random altitude z. The top of the slab sits at z plus whatever this distance is. If this is, z plus dz. And so the pressure at z is going to be greater than the pressure at z plus dz because, like I just said, when you're when you're standing here, you've got more of the atmosphere on top of you than when you're standing higher, when you're standing here. And so as a result of that, there's going to be a pressure gradient force because the pressure at z, the pressure here at the bottom, this upward pressure force, is greater than this pressure force here, z plus dz. So in theory, if you have a greater pressure here than here, then there's going to be a pressure force, and this slab of atmosphere should be shooting wildly in that direction. And this is known as the pressure gradient force, and this pressure gradient force is directed upward. However, this must be balanced, right? Because we know that the atmosphere is not flying up and up and up. So, what happened there? Okay, sorry, let's stay here for a second. Okay, so the pressure at the bottom of the slab is greater than the pressure at the top of the slab. And so that has to be balanced by something. And what it's balanced by is the weight of the slab itself. Okay? So what does that mean? So if the net upward force on the slab is equal to the net downward force on the slab, then what we say is that the atmosphere is in hydrostatic balance. So let's just take a look at that. What does hydrostatic balance mean? Okay. So the fact that pressure is greater here than here means that you have to have, so that you've got this desire to be pushing things up, so you have to have something else, so that this pressure force at Z plus Z dZ plus something else must equal this upwards arrow. And the something else is the mass of the slab. So this pressure force plus the mass of the slab equals this upward pressure force. And so then everything's nicely balanced. And this is hydrostatic balance. So the way we get at that is the mass of air in the slab is rho times dz, where rho is the density of air at height z. And so the downward acting force on the slab is going to be g, where g is the acceleration due to gravity at height z, times rho dz. Okay? And so the change in pressure from Z to Z plus dZ must be negative, right? Because this number is greater than this number. Okay, so the difference has to be negative, minus dP. And if we keep going, we can do some rearranging, we can do some algebra, and you end up with the assumption that if hydrostatic balance is reached, then minus dP, the pressure gradient, must be equal to G times rho dZ, okay? And that's basically saying in mathematical language that this pressure at Z, that wants to lead to an upward force, because this pressure at Z is greater than this, is balanced by the mass. So this mass force plus this must equal this. So you do a bunch of rearranging and a bunch of algebra, and you end up by saying dP dZ, the change in pressure as a change in altitude, is equal to minus g rho. So you've now simplified to something fairly straightforward, where g is the gravitational constant and rho is the density of air. And this is known as the hydrostatic equation. Okay, so the hydrostatic equation, which we just showed, which is that you have this pressure gradient that's balanced by the mass of the slab of air, is used in conjunction with the ideal gas law to derive what we call the barometric law. And this equation here is the barometric law. So what this is saying, and I've simplified a couple of steps here because this class isn't about sort of deriving equations in math. So the pressure at altitude Z is equal to the pressure at the surface times e to the minus z, so that's your altitude, over this value h. And this value h becomes very interesting. This value h is known as the scale height. And this is described in a lot of physical applications. In this case, we're going to use it to describe a feature of the atmosphere. So you can see the influence of the ideal gas law here, because you've got R, the ideal gas law constant, you've got T in temperature, you've got the average molecular weight of air, and G is the acceleration of gravity. So R is a constant, MA is basically a constant, right? The average molecular weight of air isn't changing, and G is constant, which means that this H scale height value is only varying as a function of atmospheric temperature. Okay, so that's all that this H component is. The other interesting thing about this equation, this barometric law up here, is it explains why there's an exponential dependence of pressure on Z, right? So, because right here you've got your exponential dependence of pressure that you calculate is on e to the z, so it's not a linear relationship. Okay, so in this case, if you take a plot like you see on the right, where the natural log of pressure is on the x-axis, so this is the log scale of pressure, and altitude on y, you get a straight line, and this slope, if you were to calculate the slope of this straight line, it's equal to h, the scale height. So what is a scale height? Why am I going through all this to sort of explain the scale height? So It's essentially the vertical distance from the surface to some height in the atmosphere over which density and pressure fall by a factor of 1 over E. And as you keep going, if you go another scale height, density and pressure fall by another factor of 1 over E, and to a third scale height, etc. So the way that I always like to think of the scale height is it's the degree to which the atmosphere hugs the planet. And so at the surface, at elevation 0, your density is whatever it is, rho 0. And at an elevation of h, a scale height of h kilometers, whatever that number is, your density is 1 over e times rho, and 1 over e is 0.368. 2 scale heights out, it's 1 over e squared, so 0.135 times rho, and then 3 scale heights out, you can see here the same. All right. So in this case, what you can think of is from the surface to 1 scale height, the atmosphere has essentially constant density out to an elevation of h. So it's like a slab of constant density. So since scale height is temperature dependent, we can estimate it fairly easily. So if we assume a mean atmospheric temperature of 250 Kelvin, which if you go back and look at the temperature profile and you look at the range of tropospheric temperatures and you kind of pick the middle, it's about 250 ballpark. So at that ballpark temperature of 250 Kelvin, we can calculate that the scale height of the atmosphere is 7.4 kilometers. So for every 7.4 kilometers rise in altitude, the pressure and density of air drop by a factor of 2.7. And it's essentially, scale height is a general way to describe how a value fades away from something. And it makes life really easy for doing sort of big picture, back of the envelope calculations. To assume these constant slabs in the atmosphere as opposed to having to do every calculation at every elevation in the atmosphere. Okay, so how do we functionally use this? And one of the reasons I've been building this up is because it's a nice way to talk about the sea breeze circulation. So some of you might be familiar with experiencing the sea and land breezes. So if you've ever spent time in a coastal location, and you have to sort of give Cape Town a break that it isn't always like this, because Cape Town has a massive mountain sitting there that gets in the way and complicates things. But let's say you've been on the seaside somewhere other than Cape Town. Frequently during the day, you get a nice cool sea breeze where you feel the air coming in off the ocean. And I don't know if any of you have noticed, but it frequently in the evenings, that cool sea breeze goes away and you end up with a land breeze. Well, why is that? So in general, you can describe it qualitatively and say that warm air over the land rises during the day and it's replaced by cool air from the ocean. And then at night, that process reverses where the land cools off and dense air sinks and it flows towards then the warmer ocean. But we can also describe this phenomenon using what we just learned about scale height and pressures in the barometric law. Okay, so I'm going to step through this example where we have our nice model parameterized. This is our sea here, and then this is our land. So you have to use your imagination in this diagram. And so in the initial conditions, the temperatures over the land, the atmospheric temperature over land and atmospheric temperature over the sea are completely equal, which I've denoted here as temperature land and temperature sea, so they're equal. And there's equal pressures over the land and over the sea. So the pressure over the land and the pressure over the sea are equal. And there's no wind. So since temperature and pressure over the land and the sea, the total air columns are the same. So we can also assume that at the surface, so the pressure at 0 altitude over the land is equal to the pressure at 0 altitude over the surface. So if we were to make a plot of the natural log of pressure as a function of altitude, and we were to plot a line for the sea and a line for a line for the sea and a line for the land, those lines would be identical. And that's what you're seeing here on the right. The land and the sea have been plotted. The lines fall right on top of each other, and they have a slope of minus h, which is the scale height. Cool. So now we've established the system. Let's perturb the system a bit. Okay, so now we have to assume it's a hot summer day. And so the land warms up more than the sea, right? The sea has a very, very high heat capacity. And so it takes a lot more solar energy to raise the temperature of the sea than it does to raise the temperature of the land. And so now we've got a new situation where the temperature over land is greater than the temperature over the sea. And remember that scale height is temperature dependent. So now something's going to be different. Okay, so there's a direct linear and positive relationship between temperature and scale height from this equation right here. So as temperature goes up, scale height will go up. So we've just said because of the differing heat capacities between the sea and the land, the temperature over the land is now greater than the temperature over the sea. And so the scale height over the land must be greater than the scale height over the sea. And so if we take that information and we look then at this equation, so now if h has increased, then an h over the land is greater than h over the sea, then pressure at a given altitude z is also going to be greater, which means so the pressure at a given altitude of z over the land is greater than the pressure at a given altitude z over the sea. And that is assuming that you're at the same height. And in this case, we are indeed assuming you're at height. So what's happening now is you have higher pressure over the land and lower pressure over the sea. And whenever you have a pressure gradient, you're going to induce flow. So at some elevation, you're now going to have the flow, you're going to generate a wind that is going to go from the land to the sea. And this is all a result of that warming. Okay. Now, of course, above the surface, you've got at this height z, you've got a pressure difference that's causing the air to flow from land to sea. As a result, the mass of the air column over land, okay, decreases. So there's going to be, because you've got wind blowing across, you're going to have less mass here than you do here. It's going to build up, okay? And so what does that mean when you're at the surface? So at the surface, remember, the pressure at the surface is dependent on how much stuff is above you. So in this case, the column of air above you on land is now smaller than the column of air above you at the sea. So as a result now, the surface pressure on land is now going to be less than the surface pressure over the sea. And if you have higher pressure over the sea and lower pressure over the land, then now you're going to generate a flow in this direction. So at the surface, you're going to have a flow from the sea to the land. And at height z, at elevation, you're going to have a flow from land to the sea. And then, of course, you're going to have this sinking and rising of air masses to balance it out. Okay. And if you look at that in the plot on the right, what you see then is for the land, the relationship of pressure and altitude as compared to the sea has changed. So now at a height of z equals 0, which is here presumably, the pressure at the sea is greater than the pressure over the land, whereas at a height of z up here, the pressure over the land is greater than the pressure over the surface. And so we've got these differing flows from land to sea and from sea to land, which on this diagram over here sets up this sea breeze circulation. Okay, so now this is looking at it again sort of qualitatively. So this kind of sea breeze idealized circulation sets up and extends usually about 10 kilometers horizontally across the coastline and about 1 kilometer vertically, just to give you an idea of the scale of this kind of setup here. And so you'd have higher pressure here and lower pressure here, and then higher pressure here and lower pressure here that's helping, sort of establish this circulation. So then what happens at night? Okay. So then at night, again, because of the heat capacities of the land and the sea, the land cools much faster than the sea. And so as a result, you end up with this circulation reversing itself, where you've actually got higher pressure here and lower pressure here, and higher pressure here and lower pressure here. And you can go back through and see if you can make sense of why the land breeze, is dominant at night as these temperatures change. Okay, so the take-home messages here are that atmospheric pressure decreases with increasing height above the ground, that the atmosphere has a constant density and sort of, you can think of it as a constant slab of everything out to an elevation of h, which is the scale height, which is on average just over 7 kilometers. And that the sea breeze circulation is a nice illustration of the barometric law, and the establishment of the sea breeze is directly related to things such as the scale height and the impact of temperature on scale heights and those pressure relationships. Cool, so that's the end of pressure.